Okay, now let us see another example here. It says the diagram below shows a body of mass 10 kilograms freely suspended from a light. Light means that its weight is negligible, that's it. Of natural length 0.5 and modulus this. So they are giving us the natural length of the spring. So the RL is 0.5 meters, and then modulus is going to be 25 newtons. Okay. Find the extension in the spring when body at rest. So in part A, now this is the spring they are giving us. I'm trying straight here. I'm going to be having the 10 kilogram mass there. Of course, there is going to be weight acting on it, which is 10 G. Of course, you're going to be having tension, which is acting upwards, and in that order. So at rest means that the body is in equilibrium. It means that now this tension that is pulling this up, the thrust that is pulling it up is going to be now our T is going to be equal to 10 G. So do that from T equal to lambda x over L. We have this, we have this, we have this. We want to get our x from there. So from here, you start that we're going to be having 10 G equal to R lambda, which is 25 G x over 0.5. So from there, I think we start this G is going to vanish. So from there, our x is going to be this is going to be 5 divided by 25. So here I'm getting 0.2 meters. Simple. Then part B, body top of the spring is moved upwards at a constant velocity. So when you move it upwards, the tension is going to act at constant acceleration, at constant velocity. So that constant velocity means that acceleration is 0. So from RFR equal to MA, what's going to be pulling it up is T. So you have T now minus this of all opposing to D, then is equal to the mass, which is 10 times acceleration, which is 0. See this that our T is going to be D. And if you put it there, so 10 D is going to be 25 D x over 0.5. This is still that our x is going to be 0.2 meters. Okay, part C, I'm telling us that top of the spring is moved upwards at a constant acceleration. At a constant acceleration of, now they are giving us acceleration as 4.9 meters per second. So it means that now the acceleration is acting upwards. What is acting upwards? You see, basing on this, of course, we're using Newton's second law of motion. So when it's acting upwards, what's put in there is T, that which is pulling it up in that upward acceleration, minus this one is opposing, is equal to the mass, which is 10 times the acceleration 4.9. From here, so our T is going to be 49, then plus 10 G. Okay. 10 G, this is going to be, so my T here is going to be, if I substitute, you see 98 plus, which is 147 newtons. Then, if I substitute from here, T lambda x over L, I have 147 equal to 25 G, then x over 0.5. From here, my x is going to be 147 and 0.5 divided by 25 times 9.8. And so from here, our x is going to be 0.3 meters. In part B, they want us to get when the spring is being moved in the constant acceleration now it's being moved downwards. What's pulling it downwards? I think you see now what's pulling downwards using the Newton's second law of motion, ma. So what is pulling downwards? The acceleration will be downwards. We are going to be having now 10b minus, now this will be opposite, equaling to 10. The acceleration is 4.9. Or if you want, you can consider it as deceleration and then you put here negative 4.5. It will also give you the same answer. So if that's the case, now you see we are going to be having now 10 times 9.8 the key, 10 minus 49 equaling to our t when I bring this side. Then I take this side. So from here, our t is going to be 49 newtons. So I'm in the substitute to my t equaling lambda x over L. This is 49 equaling to 25b x over 0.5. I cross multiply and I divide over 25 times 9.8. So my x is going to be I'm getting 0.1 meters. So that's what we had for that spring. As long as you need to know what you want, you had to know is what happens at constant velocity. At constant velocity, acceleration is 0. Put in to get that answer. When we have acceleration now, you use Newton's laws of second motion, even it's what we have been using here. But for constant velocity, acceleration is always 0 because acceleration is the rate of change of velocity. If there's no velocity, there's nothing in the velocity, acceleration is 0. Deceleration, or when it's moving downwards, it's decelerating. If you consider it as a deceleration, then you take the acceleration to be negative. Or you can consider just basically going downwards. This is pulling, this is opposing, equal to mass times acceleration. So that's what we had. I wish you well.